Let's build the linear regression model. The syntax for building the model is you need to use the LM function. Alternately, you can use the GLM function as well. Both of it would work. The first argument you need to put is the formula for the equation. Here, the formula is MPG is a function of weight and HP. This is the tilde notation that is present just before the escape key on your keyboard. You also need to specify the data argument where you pass the data frame that contains these variables. Let me run this. Now the model contains the call, that is the formula that you had used, and the coefficients of the respective variables. How you can interpret these coefficients is MPG equals to the intercept, that is 37.227 plus WT into the coefficient minus 3.877 plus HP into the respective coefficient minus 0.03177. This is the resulting model equation that LM function has fitted. Now this is not all the information that is useful. There is more to it. Let's see what they are. If you look at the summary function displays a number of useful information. It contains the residuals. It also contains, apart from the coefficients, it contains the standard error, t-value, p-value, the respective stars, residual standard error, multiple R square, adjusted R square, F statistic, and the p-value of the model itself. Let's understand them one by one. The first thing that you need to check for is the sign of the coefficient. Why? Because this sign should match with the sign of the correlation that we had computed before when we did the exploratory analysis. If the coefficient sign does not match the correlation sign, there is something inappropriate happening in the model and you need to review the variables that you have in the model. Second important thing is you need to check the p-values. P-values are written over here, and you also have the significant stars besides every p-value. You should ideally have at least one single star. 3 stars is very good. Why this is important is only if the respective term in the model is statistically significant, it will have a low p-value, lower than the respective significance level that you have assumed. Typically, the significance level is 0.05. Now, what is happening underneath is for every variable, there is a hypothesis test being conducted, and the null hypothesis of that test is the beta coefficient of the respective variable is 0. If the p-value is not less than the significance level, that is, if it is not less than 0.05, you cannot reject this hypothesis. As a result, it means that the estimate, the respective coefficient your variable has, does not play that much of a role in determining the output value of your model. In most cases, or typically, you are well off removing that variable from the model itself. Next thing is the standard error. It denotes how much the beta coefficient your model has computed can vary. The lower the standard error, the better it is. And this standard error is directly involved in computing the t statistic. T statistic is nothing but the beta coefficient, that is the estimate that you have here. In case of intercept, it's nothing but 37.227 by the standard error. It will give you the t value. And from this t value, the p values are directly computed. So in a sense, the beta coefficient, the standard error, the t value, and the p value are directly affecting each other.